How's everybody? I like that song because it's, well, first off, it's, to me, it's just excellent because, yeah, I don't think you can get much better as musicians. It takes a lot of work to get that far there, doesn't it? That's right. It takes a lot of work to do anything. A little inspiration. Hopefully you have some goals you're working towards. Substitution reactions. Let's see where we're picked up at. This week in lab we're doing elimination reaction, double E2 elimination reaction. Using the dibromide you made about 6 weeks ago. That'll be your starting material. That's 2 bromines, 2 leaving groups. Report for the shaken not stirred due this week in lab. Formal report. Any questions before we get started? Let's see where we left off at. Substitution reactions, effective nucleophile, nucleophilic strength. Sterics really affects SN2, both in the substrate of the leaving group and also the nucleophile. Range each of the following for nucleophilic strength. Number 2, which one is the strongest nucleophile? Strongest nucleophile.
NH2.
Anybody?
NH2. NH2.
KNH2.
KNH2. Why that one? Well, let's get rid of these, right? That's N minus, that's O minus, that's O minus. These are Cl minus, F minus. Potassium is a spectator ion. Okay? NH2, why?
Least electronegative. So least electronegative.
Least electronegative. They're all anions. Least electronegative, so it's going to be the worst pair. It's going to hold it the least. Okay? That's NH2 minus. Yeah, it's a very strong nucleophile. And I wish it said from strongest to weakest. Weakest to strongest. 1, 2, 3, 4. So that's 5. Okay, what's next?
methyl.
OMe.
Oxygen or halogen?
Oxygen.
Oxygen. O-methyl or O-T-butyl?
O-methyl.
Yeah, why is this less nucleophilic?
Steric.
More sterics. Has a T-butyl group on the oxygen. So this would be 4. This is actually 3. It's still an O minus. Let's start. Let's say which is the worst nucleophile.
KN.
Worst nucleophile. Yes. Worst nucleophile is going to be F minus. Cl minus is not as electronegative, so it doesn't hold the lone pairs as tight. Then the oxygen, but the less sterically hindered is going to be more nucleophilic. So this is less nucleophilic, more nucleophilic, and most nucleophilic. Okay, nucleophiles. Summing it up. What type of nucleophile can participate in an SN2 reaction? The answer is strong ones. And you can put only strong ones. Now, this is a wee bit general statement because there are some exceptions. But that's a good starting point right there. You need a strong nucleophile. Why do you need a strong nucleophile? Question. Is the nucleophile involved in the rate determining step of an SN2? Yes. To be involved in the rate determining step, it has to be able to do something. It has to be strong to do that, to be involved. Okay? That's the slow step, that's the major important step, that's the difficult step. If it ain't strong, it ain't going to be able to do that. Okay? The nucleophile is involved in the rate determining step of an SN2. Which ones are strong? Well, we just went through how to judge relatively which one's stronger. But Cl minus, do we call that strong? There's a difference between an absolute statement and a relative statement. Well, I'm going to tell you which ones are strong, but this is also going to be a general statement. There may be some exceptions, but it's a good starting point. And the strong nucleophiles is the same as we said for strong bases. And here's your strong nucleophiles. Anions or sp3 nitrogens. sp3 neutral nitrogens. Possibly sp2. It's the same thing we said for bases. Anions, okay? Now the exception to that is your anions of strong acids tend to be weak bases and also tend to be sort of weaker nucleophiles. So what I just told you is Cl minus a strong nucleophile. Is it an anion? That's a strong nucleophile according to what I just told you. Problem is, that guy is not that strong of a nucleophile. It's not that strong. What about I minus? Is that a strong nucleophile? Well, according to the definition I just told you, is it an anion? Yes, strong nucleophile. Now that is actually a pretty good nucleophile. Compared to this, we see why, because it's less electronegative. Okay? But in my definition, that is sort of it's not that strong. Okay, so there are some exceptions, but it's a good starting point. Anions, sp3 nitrogens. Okay, let's classify these as weak or strong. This guy, it's got lone pairs, it could be a nucleophile, weak or strong. Is it an anion? Is it sp3 nitrogen? So what is it? Weak. Weak or strong? Weak. Weak or strong? Ah, let's get rid of that. That's O minus, right? Okay, is it an anion?
Yes.
Weak or strong?
Strong.
Strong. Weak or strong? Why? It's not an anion.
sp3
It's sp3 nitrogen. Okay, that nitrogen is a terrible parent. Let's just lone pairs get out there and do backside attack. Weak or strong? Ah, sp3 nitrogen. Is that an sp3 nitrogen?
No, it's sp2.
What type of orbital is a lone pair in?
Orbital.
LP and P orbital. An LP and a P orbital is typically not reactive. It's not basic or nucleophilic. It's busy doing P orbital stuff. Resonance. A lone pair that's conjugated is typically not reactive. There are exceptions to that. There's exceptions about everything we say. But a good general statement is, your first thing is going to say, I don't think that lone pair is reactive. It's conjugated. It's being involved with resonance. Now, how much resonance? When you delocalize it, you put a negative on carbon, and carbon doesn't like negative. So it's not delocalized a lot. But now we're getting into trying to explain why, what. But our opening statement is that's weak. KCN, that's one of my favorite nucleophiles. KCN. Y'all remember KCN in the Sunshine Band? Everybody's ever heard of them? KCN. Well, let's get rid of that. A cyanide, triple bond, lone pair. Cyanide, strong nucleophiles, good nucleophile. Water. Is it anion? sp3 nitrogen? No, it's weak. All these can be nucleophiles because they all have lone pairs. Okay? Are you going to do an SN2 with water? Not if it requires a strong nucleophile. Will you ever see an SN2 in water? You may see one. Very high temperature, like 400 degrees, very harsh conditions. Somebody may describe it as an SN2, but the opening statement is going to be tough to do an SN2. Okay? It's very general, but it's going to get you the answer 95% of the time, and it's a starting point. Questions about this? You've got to have a strong nucleophile for SN2. How do you recognize strong? Also, relatively, which one of those anions is stronger?
I
I minus. I minus is actually a great nucleophile. Okay, let's look at various examples of SN2. Various examples. First, alkylation of oxygen. First, alkylation of carboxylic acids. It's a precise example of number 1, so it's 1A. Alkylation, we're going to put an alkyl group on the oxygen. Put an alkyl group on this guy. Ultimately, this is going to act as the nucleophile. And we're doing SN2s. Can this do an SN2? It's weak. Okay. Can we turn this into a better nucleophile? Would this be a good nucleophile for SN2? Anion, yes. Can we turn this into this? Yes, that's just an acid-base reaction. Very importantly, if you treat this guy with a base, what's your favorite base? Sodium hydroxide. Treat this with sodium hydroxide. The hydroxide will take the H, electrons stay behind. We get that plus water. And the sodium ion sits with that. So we went from a weak to a strong nucleophile. We went from the neutral to the anion. Now it's a good nucleophile. That's easily done. So we have to generate the better nucleophile. Now we can come in with some type of alkyl group with a leading group. And these electrons can come in here and do our good old SN2, backside attack, kick that off. And we make this bond here. I like to highlight the bonds we make sometimes. And we made that product. And what have we put on the oxygen? An alpha group, which in general is called alkyl. An alkane group, called alkyl. We've alkylated the carboxylic acid. We turned the carboxylic acid into what functional group? Ester, right? Common way to make esters, starting with the carboxylic acid. We first had to sort of activate or generate the good nucleophile. Then we do our good old SN2 reaction. Okay, what about other oxygen functional groups? What about alcohols? Take this alcohol here, sodium hydroxide. Can we treat this with sodium hydroxide and get this O minus? So even though this is showed as O sodium, we know this is O minus and sodium plus, right? Okay. Now up here we use sodium hydroxide. Because up here, what was our equilibrium? pK of this is about what? About 5 plus water. What's the pK of the acid over here? Water is 16. Which side's favored, 5 or 16? Weaker acid is favored. That side's favored by 10 to the 11. It's a huge number. How about down here? This plus this would give this plus water. There it is. Is this favored? Obviously not, because of the X. pK of 16. See, this is 16. This is a lot less acidic than that. That's called a carboxylic acid. Alcohols are less acidic. Which side's favored, 16 or 16? It's 1 to 1 in equilibrium. Now you have half of this, but you also have half of this. And in practice, it doesn't work. You have to fully form this in practice for it to work. You need a pK difference of at least like 2 to 3. In the end, this is not good because this is less acidic than that. Or you can say the base is not strong enough in this case. So how do you make anions of alcohols? You can't use hydroxide. Instead, there's a couple of ways. You can use just sodium metal. This is not sodium ion, it's sodium metal. Oxidation state of 0. If you take an alcohol and treat it with sodium metal, you'll get these sodium... By the way, what do you want to call this? What do you want to call the O minus? It's an alcohol. What do you want to call this guy? What do you call this? Sodium hydrogen oxide? Hydroxide? Well, what if this had an R group? What's your favorite R group? Maybe it's isobutyl. Some type of R group. R group is what? An alkane? Sodium hydrogen oxide? Sodium al... It's called alkoxide. It's the alkoxide. That's an alkyl group on the oxygen, not a hydrogen. You can't make alkoxides using sodium hydroxide, but you can make them using sodium metal. And if you look at this and balance it out, the byproduct is not water or anything, but it's hydrogen gas. This reaction is actually a redox reaction, and it generates hydrogen gas. Now you can balance this if you want. You got 2 H's over there, you got to have 2 of these, right? I think if you put 2 in front of everything over here, it'll be balanced. I'm not good at balancing reactions. Does that look right? Is it now balanced? I think it is. You can balance it. I don't even like to do that. It's a redox reaction. It's not an acid-base reaction where we can move arrows. It's probably a radical reaction. Redox. Something's reduced, something's oxidized. Oxidation state of the sodium is 0. What's the oxidation of the sodium now? +1. Sodium has been oxidized. What's been reduced? Here, the oxidation state of the H is +1. What's the oxidation state of the hydrogen here?
0.
It's in the elemental form. 0. The hydrogen has been reduced. The sodium has been oxidized. Again, it's not an electron-moving acid-base mechanism. It's a radical redox reaction. But guess what? You take an alcohol and you put in sodium, and we may do this in lab this week. It'll start bubbling. What are the bubbles?
Hydrogen gas.
Hydrogen gas being generated and bubbling out. But we're not worried about that. We generate our alkoxide, which is a better nucleophile. And with this guy, we can then do SN2. So we can generate the sodium alkoxide. Okay, same thing. I'm just showing the spectator ion and not showing the charges, but it's charged. Then we throw in some type of carbon with a leaving group. So we can, this is a nucleophile. What else do you need in the reaction? You need a carbon with a leaving group. Now we can come in here and boom, kick that off, make that bond. Good old SN2. Now if sodium is sitting here, what do we show as complete? What else is formed here in a balanced reaction? Sodium chloride. SN2. And that's analogous to above, except we had to use a different base. Sodium is considered a base here. What have we done in terms of functional groups? We started with an alcohol. What is our product? No longer an alcohol, is it? What is it? Oh, wait. No, alkoxide is a negative oxygen. It's no longer a negative oxygen. This was the alkoxide. What functional group is the in?
Ether.
Everybody knows what that functional group is?
It's an ether.
Oh, like
Ether.
yeah. Oh, yeah.
Yes. Thank you. Ether. Our exam is about 3 or 4 weeks. That should be an easy question, guys. Okay, what about phenols? By the way, this process is often called a Williamson ether synthesis. Some chemist by the name of Williamson said, hey, if we take an alcohol and make the base, the alkoxide, and then throw in a carbon relieving group, we can get the SN2 and we can make an ether this way. Making ethers from alcohols is typically called the Williamson ether synthesis. Okay, we can use phenols. Now, phenol is much more acidic than an alcohol because we know we have a resonance stabilized anion. Phenols, you can use sodium hydroxide. That's 10, water 16. Which side's favored, 10 or 16? 16's favored by 10 to the 6. That's enough. It'll be complete. So you can do this because it's more acidic. Now, what do you want to call this? It's really not called an alkoxide. This is called a phenoxide because of the phenyl or the benzene ring. It could have been called like a benzoxide, but it's called a phenoxide. Phenyl is like an alternative name for benzene. You use the term phenyl when it's a substituent, but it's used here. It's phenoxide, phenoxide, sodium phenoxide. You can make them with hydroxide, make this phenoxide. Once you get the phenoxide made, then you can throw in some type of carbon relieving group, like methyl iodide. Okay, this is minus. These electrons attack here. That's not really even drawn out right, is it? I mean, right? Boom. Take it off. Great leaving group. No sterics here. Very nice reaction. Make the methyl ether. Put an alkyl group on the oxygen. You can make rings like this. You take this starting material here, treat it with sodium metal, you get this plus sodium bromide. What is sodium going to do to this? The only thing you know is sodium reacts with alcohol to do what? Sodium reacts with alcohol to generate what?
Sodium.
It generates the alkoxide. Get rid of that, you form hydrogen gas. Okay? So if you want to completely balance this, you can also see hydrogen gas. But here, what can this do? These electrons can, boom. This is an internal SN2. Make ring, and then you have a 1, 2, 3, 4, 5-membered ring with oxygen part of the ring. So bromine used to be attached here, but now the oxygen is attached there. So we make that bond. We produce Br minus, but the Br minus can sit with the sodium plus, and we also generate hydrogen. But we can make this ring by an intramolecular SN2. Does that look straightforward? Just an intramolecular version. Need to be able to go backwards here and do propose synthesis. How about this? Provide a Williamson ether synthesis of the following compound. Now I could have said provide a high yielding. There may be more than one route. So can you show a synthesis of that compound, that ether? What are the components of Williamson ether synthesis? Start with the alcohol. Could be a phenol, which is a special type of alcohol. Generate the alkoxide or the phenoxide using the appropriate reagent. And then then you bring in an alkyl portion, and that alkyl portion has what on it? A leaving group. So can you show that synthesis? Also, usually synthesis, you put together smaller fragments to build a larger molecule. When you're doing synthesis, it's good to, on your paper, in your thought process, sort of go backwards. And when you do a double-headed arrow like this, this is meaning you're going backwards. It's called retrosynthetic analysis. Let's do some analysis of this. What are some possible ways to approach this? We're really going backwards. This is a retrosynthesis arrow. If we're building this up, if we go backwards, that means we break it down. Where do you want to break it at? Do you want to form this bond here, this carbon-carbon bond? No. It's going to be much easier to form, especially if you're doing a Williamson ether synthesis, you need to be forming an O carbon bond. That's what that is. What if we form this bond and go back to oxygen here as an anion? Plus what? 3 carbons? Propane? Go back to this. Now if you go forward, we can say, if we go forward, will this react with that to give that? What's the issue with what I'm showing here?
No leaving group.
No leaving group? I just need 3 carbons. I can't just react with propane? Why not? How many H's here?
2,
How many H's here?
3.
3. I have to lose an H. Hydrogen is not a leaving group. And it ain't going to just disappear. But I get this all the time. Hey, I just need a 3-carbon fragment, so I'll just throw propane. But how are you going to make that bond? How is this going to react here? It's not going to react. We need a leaving group here so we can have this attack here and make the bond. If you think about it, how else would you make the bond? Any of our substitution reactions, there's only 2, both of them involve leaving groups. Substitution. H is not a leaving group. We need a leaving group here. What's your favorite leaving group?
Chlorine. Chlorine.
Chlorine? Why is that your
Iodine.
favorite? Because it's the cheapest?
No.
It's not really the best. It's reasonable, but
Iodine.
iodine's better. Iodine's a little bit unstable, though. Bromine is my favorite. Any others?
NH2.
Tosylate? Anybody have tosylate as their favorite leaving group? Tosylate. Yeah. How about a O-tos here? Any leaving group. Then we can have this come in here and attack this carbon and kick off the tosylate or whatever. Okay? You need an LG. Would this give that? Yes. So this is going forward. This is our backwards thinking. Okay, how are you going to make the alkoxide? Because maybe the instruction says starting with all neutral compounds. Well, that's not a neutral compound. How are you going to make that? This react with what? Well, sodium. Not sodium hydroxide. What about this? What if the direction said starting with any alcohol? You must start with any alcohol in your synthesis. Well, there's the starting alcohol. Hold on, that's not an alcohol. Tosylate. How do you make tosylates? If you had this alcohol, could you make that tosylate? What would you react this with to make that tosylate? Well, just put a question mark there. You need to make sure you know how to make tosylates. Is there another way to make this ether? Other than this reaction? Did anybody consider making this bond over here? And having maybe a leaving group here and how about that? Would this give that product? Yeah? Yeah.
Does the yield change? Like the amount of...
Well, let's analyze that or assess it. Which do you like better? Yeah, 2 different ways to give that ether. 2 different syntheses. Which do you like better? Leaving group is on a secondary carbon, where here the leaving group is on a primary carbon. Can you do this? Can you do SN2 when the leaving group's on a secondary carbon? Yeah, you can, but it's the most difficult. What if this was a tertiary carbon? Oh, then that would be bad. Then you would only have one choice. I kind of like that one over there better, because the leaving group, the substitution of your leaving group is very important for SN2. I'd rather have my leaving group on a primary carbon, but that doesn't mean this can't work. If this was on a tertiary, it would not work. So you need to be able to think going backwards, and that's called synthesis. Making molecules, proposing synthesis. So that was oxygen. What about sulfur? Can sulfur be a nucleophile? What if this was S minus? Would that be a better nucleophile or worse nucleophile compared to O minus?
Isn't that supposed to be positive?
What?
Isn't that supposed to be positive?
S is supposed to be positive?
Okay.
No, we're talking about being nucleophile. What are good nucleophiles? Anions or sp3 nitrogen? I'm asking you to compare. What if this was S minus instead of O minus? Would it be a better nucleophile or worse nucleophile?
Better.
Be better. Why?
Less electronegative.
Sulfur is not as a, doesn't hold the lone pairs as Tyler. Yes. S minus is an excellent nucleophile, especially compared to O minus. Now, a neutral sulfur, is a neutral sulfur a good strong nucleophile for SN2? Neutral sulfur? Like that there. Is that a strong or a weak nucleophile?
Weak.
It's weak according to our definition because it's not an anion or it's not an sp3 nitrogen.
It's stronger than
But it's stronger than an OH. Actually, a neutral sulfur is almost a good enough nucleophile from SN2. It's one of those, well, your general statement is certainly S minus is a great nucleophile. In the end, your body uses sulfur as a nucleophile in lots of biological processes. For example, glutathione. This is glutathione. It's a tripeptide. It serves as your body's sacrificial nucleophile. For example, methyl quite toxic. Because if it gets in your body, things like DNA, which have amino groups, this may be shown. Lots of your biological molecules have nucleophiles in them. And if you ingest or inhale methyl iodide, you'll start alkylating your DNA, put a methyl group on your DNA. And then you're going to start causing cancer and whatnot, or stuff. Your body has some defense mechanisms for, what do you want to call this, a general name for this? Electrophile. It's very electrophilic. It loves these electrons to come in here and do this. This is a defense mechanism for potent electrophiles. What happens is this guy comes in here and attacks and keeps this from happening. It'll attack. Now this may be in a negative form because this has a pKa of about 10 to 12, and in certain positions in the body, it may be in the anion form. And the anion form is certainly a stronger nucleophile, but it's a sacrificial nucleophile. And once this reacts, it doesn't matter. Then your body just flushes this out. It does its role. Mucomist. Mucomist is actually a drug that's used. You may know what mucomist is used for?
used to HTTP decisions.
You what?
Produce the mucus in your nose.
No, I mean, that name might tell you that. I don't know if it's used for that or not. But mucimist is used when you, to treat overdoses of Tylenol. If you take too much Tylenol, your body converts it to a reactive species. Converts it to a potent electrophile. And then that species starts reacting with nucleophiles in the liver. Okay, lots of nucleophilic things in the liver that are good, like proteins in the liver. When that reacts with the thing that is formed from Tylenol, then you get liver toxicity. What they do is they give you this, and this reacts with the thing. That's sulfur. It reacts and it clears it out of your body. And it keeps your liver proteins from reacting. Sulfur is used as a good nucleophile. Again, these are in the neutral form, but these could become minus in the body under certain pHs. So your body actually uses sulfur as a nucleophile. We saw earlier it used it as a leaving group, the SAM. Okay, oxygen, sulfur. What about nitrogen? Nitrogen. If we do an SN2 reaction with nitrogen, we're again alkylating. And it would be called a direct alkylation of an amine. This reaction is possible. It does have a drawback that can lower the yield. We'll talk about that. Let's first look at the reaction. Here I have ammonia. And here I have a carbon with a leaving group. Now in this synthesis I put the nucleophile on the line. I could have put the nucleophile here and the carbon with the leaving group here. It doesn't matter. Here ammonia is the simplest amine. Is it a strong nucleophile? sp3 nitrogen. These electrons attack here, kick that off. What does this give? It gives this here. Because the nitrogen lone pair is now bonded to the carbon, we generated Br minus, but importantly the nitrogen is now positive. Because if you start neutral, it goes positive. And for this to become neutral, we have to lose a proton. So we actually need a base to remove the proton. Now, can Br minus remove the proton? Theoretically, it can. We can show Br minus taking the H, leaving the lone pair behind, and you would get this. But look at this. We're saying we generate this plus HBr. The pK of this is about 10. And the pK of this is like -5. It's a strong acid. Which side's favorite, 10 or -5? The weaker acid, 10. So, is this going to go this direction? Is Br going to remove the H? No, it's mainly going to exist this way. This will just take the H back, and it mainly will sit here. Br minus is not strong enough to take the H. We'd have to include some other base to take the H. You can include it in the reaction, or you can do it after the reaction, like in your workup. In the end, when you get this product, what have we done to the nitrogen? We put an alkyl group on because this has the alpha group. Where here, there was no alkyl. We've alkylated our nitrogen. And we did it directly because I'll show you indirect routes. Direct alkylation of amines, including ammonia, can be done. Problem with this reaction in practice is you often get polyalkylation. More than one alkyl group. How could that happen? The ammonia can act as the base. Ammonia can take an H and make ammonium bromide, and this generates the amine again. The amine can then react again to put on another group. And that can happen in the reaction because as soon as some of this is formed, the ammonia can move over here and start acting as a base. Polyalkylation is often a problem, although it's not always. Let's look at the very first page of this handout. What are they doing here? They're going from 31 to 32. They have a carbon with a leaving group. Now it's not an O-tosyl, it's a mesylate. I told you that's a variation of a tosylate. So they have a leaving group. They want to get this nitrogen here, so they bring in this guy, which is a sp3 nitrogen. It's a good nucleophile. This comes in here, kicks off the leaving group. And that H is there. Okay? Don't necessarily write this till you see it. That H is there. And that's positive until you remove the H. Why do you think they include potassium carbonate? What's that to do? It's a base. Carbonate takes the H. End of reaction. And just like I showed on the other page, when you take the H and leave it behind, that leaves the lone pair behind, and that gives you your neutral product. Carbonate is included as a base. Acetonitrile is just a solvent. They reflux this for 72 hours. What is that, 3 days? That'll be our next lab. 3-day reflux.
Are we going to come back after that?
Yeah, you had to come back in 3 days.
Wait, does that mean we have to come back on the weekend? Or?
I saw a reaction one time in literature, they reflux it for like a year. What is reflux? By the way, we'll be refluxing in lab this week. We haven't refluxed yet this year, this semester. Reflux is just a fancy word for boil. I'm going to boil it. But you're going to have to use a condenser. Okay, we'll be refluxing in the lab. Boil it for 3 days. Okay, long time. Why do you think it took a long time?
Reactions can be slow.
Because the reaction is
Slow.
slow. Why is the reaction slow? Can you give any hypotheses of why it might be slow? Let's see, the leaving group is on a primary carbon. That shouldn't be slow, should it? How can you get faster than that? What about our nucleophile, though? It's a secondary amine. Now, if you go back and look at amines, when we looked at the nucleophiles, what do we say about tertiary amines? We said tertiary amines are very slow, and they're actually used when you don't want substitution. Secondary amine will still react, but it may be a little slower. Primary amine is going to be faster. My argument would be is, why is it slow? Probably because this is a secondary amine. And it's got substituents here. So they included base. Okay? It can be included in their reaction. They just included the base in their reaction. And so at the end, they had the neutral product. The nitrogen with the extra alkyl group on it. Okay. You can certainly do this directly in the there's drug syntheses that show it directly. Polyalkylation, though, is often a problem. And thus, sometimes we see indirect routes. Indirect routes. This is an indirect route to make the same product, but without getting polyalkylation. It makes use of azide. What's the charge at N3 here? Negative, because sodium is plus, N3 is minus. We do a Lewis structure of N3, which I think was in test 1 homework. It's actually got 3 charges. There's a Lewis structure for N3. The net charge is minus. This either N on the end can be a nucleophile, and you can get this with the N3 Lewis structure here. Basically, now you have an alkyl group here and this nitrogen neutral, but the 2 on the end each have a charge, but the whole thing is neutral. From here, if you actually take and hydrogenate this, you'll cleave off, I think it's nitrogen, but that may be reduced. But ultimately though, you leave 1 nitrogen on and you can get the same product. And you can get a good yield of this without having to worry about polyalkylation. Because this is only going to alkylate once. And so this is sort of an indirect route to making alkylamines. Also illustrates the use of azide. As we go along into organic 2, we'll see other indirect routes to make substituted amines, like reductive amination. Okay. Other indirect routes will be covered in organic 2. Okay, we're about out of time. Please look down here. Application is the idea of what a quat is. Quaternary nitrogen, bonded to 4 groups. It's going to have a positive charge. We'll look at that. Including a look at the world's most bitter compound. World's most bitter compound. All it takes is like 1 molecule to make you go, ugh.
Is it edible?
Well, they put it in things to keep you from eating it, like antifreeze. Keep the kitties from eating it. So the kitty will, ugh, and won't eat it. Okay, guys, have a good day.